right, so this is chapter 12. We're going to be looking at the senses. So our sensory receptors are cells that specialize in collecting information about the environment both inside and outside of the body. And they collect that information and then send it on to the brain for processing. And then the brain, decides what to do about that information. And so we categorize these into two basic categories, the general senses and the special senses. The general senses are receptors that are all throughout our body. They're in the skin. So when we think of touch, okay, also though inside of organs, joints, all over the body, we sense how much oxygen is in our blood. We have pain receptors. We have baroreceptors that sense what our blood pressure is, that type of thing. And then we have what we always think of as our senses, and those are our special senses. And these are going to be confined to the structures of the head. And so this is going to be sight, taste, smell, hearing. So eyes, ears, nose, mouth. Those are what we typically think of as senses, and those are the special senses. All right, look at these blocks here and see, can you read them all? Look at A on the left. What is the number? It's number 25. Can you see that? What about on the right? That one, if you are not colorblind, is 29. B, that one might be kind of hard to see. On the left there is 45. On the right is 56. And in C, on the left is 6, and on the right is 8. If you have trouble reading any of these, you may have color blindness, okay? This is caused by issues with pigments that are missing, with an absence or decrease in the number of cones that are in the eye, and we're still learning some things about color blindness. Rods in your eye detect only light and dark and are very, very sensitive to low light levels. Cones are what detect color, and these are going to be concentrated near the center of your vision. There are 3 types of cones that see, or there's different types of cones for different types of colors. So 3 types there. We have red, green, and blue. And then the brain takes the input from these cones to determine our color perception. So sensory receptors are the entrance point for information about our environment coming in and being sent to our nervous system. The sensory receptors are very diverse, but they do have particular features in common. Each is sensitive to a certain type of change in the environment. The form that information is sent to is what we call, sent to the brain is what we call sensation, okay? And our brain interprets that, and we call that perception. So sensory receptors, these are going to be specialized cells or multicellular structures that get that information in from the environment. So they receive the information. It's kind of like a car, has all those sensors to detect. If you have low oil, if your engine light comes on, there are sensors in there that detect information, and when something's changing, it's going to send information into the computer. Well, that's just like our senses in our brain. And so they're sending that information along the nervous system through neurons, and these are afferent, okay, which are going into the brain. And then again, sensation, and we think of sensation and perception kind of as the same thing, but technically sensation is what occurs when we are aware of an impulse going through, and then perception is the way the brain interprets that information. So if I take a bite out of a lemon, okay, when that taste first comes in, that is sensation. When I determine that what I'm tasting is a lemon, that is perception. All right, so this is an example pathway. If we'll look over here, let's see, we did taste, so let's look at smell. So smell, the receptor is going to be, and by the way, the sense of smell is olfaction. So you have olfactory receptors here that are going to pick up chemical impulses through the nose, all right, through those olfactory receptors, okay? And then that information is going to be sent along olfactory nerve fibers. It's going to go on through to the cerebral cortex, and then you are going to have the sensation of a pleasant smell, and then your brain, almost instantaneously to us, will perceive that you're smelling an apple. Okay, and so this chart kind of goes through all of different pathways here. All right, so these are the 5 different types of sensory receptors. We have chemoreceptors. These respond to chemicals, usually dissolved in water, but dissolved in a liquid, okay? We can even have chemoreceptors in our internal organs. These detect changes in things like oxygen concentration, hydrogen concentration, hydrogen ion concentration, which relates to acidity, how acidic perhaps your blood is, okay? Different ions like sodium and potassium, glucose, all of those really important molecules that the body needs to function. We also have pain receptors, which are also called nociceptors, and these respond specifically to tissue damage. And this is going to trigger stimuli from excess, what we call mechanical, okay, which is what we would think of as physical, electrical. So when you get shocked, actually I did this the other day. I went to unplug my hairdryer and got my finger on the metal, and that hurt, right? I felt that little shock. Thermal, so a burn, or chemical, okay? So different types of energy trigger these. Now, thermoreceptors, thermo meaning, think thermometer, temperature changes, and you actually have different receptors for heat and cold, and we'll get into those in a little more detail. Mechanoreceptors detect mechanical forces because they actually cause a change in shape. They cause something to deform or change in shape. And so you can feel something that pushes on your skin, balance, or vibrations. This would be a mechanoreceptor. We also have proprioceptors, which are not on this list, and these are important though. Changes in the tension of muscles and tendons. Proprioception is basically awareness of where your body part is in space. If I put my hand behind my head, I don't have to look to see where my hand is. I can feel where my hand is, and that is proprioception. All right, then we have our baroreceptors or pressoreceptors, and that's going to detect changes like baro meaning barometric pressure. So like in your blood vessels, you can actually detect if your blood pressure is going too low, and then your sympathetic nervous system can try to kick some things into gear to change that. Stretch receptors, so like in your lungs and your bladder, actually respond to physical stretching, all right? And then photoreceptors is another one, and those respond to differences in light energy. Stimulation in a sensory receptor is going to change the local membrane potential. We can also sometimes call that receptor potential. And that is going to cause a graded electrical current. And once that is able to reach that threshold level, the action potential will be fired. Okay. If it is another cell type, its receptor potential must be sent on to a neuron to trigger that action potential. If that receptor is not part, is going to be transferred to that neuron, like we just said, then the peripheral nerves are going to transmit impulses to the central nervous system where they are analyzed and interpreted in the brain. We sense a stimulus when that sensory neuron reaches that threshold potential and that action potential is fired. The message is sent on to the brain and interpreted. That becomes the perception. So pain is a sensation, but knowing you slammed your finger in the door is a perception. So it's a stimulation is going to occur at the same time as it takes that sensation to form. So your eyes see, the ears hear, and projection is where the brain interprets that sensation to come from the receptor that is being stimulated. So this allows a person to pinpoint exactly the region of stimulation and know where that's going to occur. We receive so much stimuli that the brain has got to be able to tune out the unimportant information that it is receiving. So we can have a reduction in sensitivity to a stimulus after constant exposure, and this is going to free up us to be able to respond to other stimuli. So this is why after a while, if you light a candle after a few days, you're no longer able to smell that candle. And so it's because you get used to that and your body says, oh, I know what this is. This is not something that's important. I'm going to shut that off. Okay. And so the sensory impulses are going to become a lot less frequent. They may stop completely, and then you also will need a stronger impulse to trigger that particular sense. So senses are associated with skin, muscle, joints, and viscera. We have three groups here that we can classify them. The exteroreceptive senses, also called exteroreceptors. These are associated with the body surface like touch, pressure, temperature, and pain. Visceral, meaning visceral, so deep internal organs. Visceroreceptive senses, also called entero being inside, extero being outside. These are associated with things deep inside in the viscera, such as blood pressure, causing stretching of the blood vessels, or those stretch receptors sensing, it's not just stretch receptors, but ingestion of a meal. So you'll have stretch receptors, chemical receptors that'll be involved in that. And then our proprioceptive senses, and that's associated with changes in the tension, basically, of muscles and tendons at joints and things. So awareness of a change in a body position, okay? pH receptors, by the way, for the visceral receptors, if you have acidity changes in the small intestines, that's an example. All right, so we have three types of touch and pressure senses. We have free nerve endings, and these are the simplest receptors. They're found between epithelial cells. These are responsible for things like our sense of itching, okay? Then we have our Meissner's corpuscles, also sometimes called tactile. These are small, flat, connective tissue cells, high in hairless portions of the skin, like the lips, palms, soles of the feet, nipples, those areas. These provide very fine touched and texture sensations. This is what allows us to distinguish between 2 points on the skin touching an object. So if I touch myself with this pencil here, this eraser, it's blunt, it's not sharp. But if I take this one, the lead, there's going to be some sticking out, and touch, I can tell that that is pointy. Okay, so it gives me that distinguishing between what's touching my skin. Then we have the Pacinian corpuscles, and these are larger structures of connective tissue that are found in your deep tissues, and this is where we sense vibrations, stretch, and heavy pressure. All right, so we've got examples here. Here we have the free ends of some sensory nerve fibers in the epithelial cells, okay? So you can see these free nerve endings. These are some epithelial skin cells here and the nerve itself here. Next, we have the epithelial cells. We have the tactile or Meissner's corpuscles, the touch receptors, and then the nerve sensory fiber here. And then this is an example of the Pacinian corpuscles, or your pressure receptors, okay? So we have two groups of nerve endings in the skin that act as thermoreceptors. We have our warm receptors, which are most sensitive to temperatures above 25 degrees, and they are unresponsive at 45 degrees Celsius or higher, okay? Anything above that, you're going to trigger pain receptors instead and get that burning sensation. Cold receptors are going to be sensitive between 10 to 20 degrees Celsius, and you can see the Fahrenheit there is on the slide as well. Anything below 10 degrees Celsius triggers, again, those pain receptors and gives you the freezing sensation. So that's why if you stick your hand in, say, a bucket of ice water, at first it's cold and then it turns into pain. All right, so it's triggering different receptors based on a range, okay? Now, at intermediate temperatures, the brain is going to receive sensory input from different cold and warm receptors. These do adapt very quickly and they don't last very long. So this is why when you jump in, say, a lake of water at first, maybe it's a little cold, and if you stay in there for a minute, you get used to it. That's called adaptation. Our nociceptors, our pain receptors, are found throughout the skin and in the internal tissues, pretty much everywhere except nervous tissue of the brain, because the brain has no pain receptors. These have a very protective function because these are stimulated when tissues are damaged, and they act to prevent further damage. Pain receptors differ from other somatic, and somatic meaning body receptors, because pain receptors do not adapt much. If they do, it's just very, very little, okay? Some pain receptors respond to different things, usually mechanical damage, although some are very sensitive to, of course, like we said, temperature extremes. Some respond to chemicals like hydrogen ions or potassium ions, histamine, acetylcholine, ischemia, which is low blood flow, or hypoxia, which is low oxygen. So a sharp pain, for example, like a muscle cramp, happens because blood flow is interrupted by contraction that is squeezing the capillaries as it stimulates mechanoreceptors. Now, people do truly have different pain tolerance or sensitivities to pain based on genetic differences that cause the sodium channels to stay open longer. All right. And so while I have a very high pain tolerance and tend to be kind of intolerant of people that have a low pain tolerance, I have to remind myself that they may feel more pain than someone else does because there is a genetic difference there. And there's actually some people with a very rare mutation that have sensory and autonomic neuropathy, which means they don't feel pain at all. And so they wind up injuring themselves very, very severely, and they have no clue that this has happened. So this is a very, very serious condition to deal with. Visceral pain receptors, these are the only receptors in the viscera that have, when they're stimulated, they produce sensations. They respond differently to stimulation than other pain receptors. They're not very well localized, and so we can often have what we call as referred pain. And this is where it feels like it's coming from another part of the body. And so you can see this on the diagram over here, okay? So localized damage to intestinal tissues during a surgical procedure may not cause a pain sensation even if they're conscious. However, if there is a more widespread stimulation, like during a muscle spasm, a strong pain may be felt. Okay, and so if you have a gallbladder issues, you may feel that all the way up here in your right shoulder. So it can be a little hard to distinguish what is causing that, but we have this map here of referred pain and where we know certain things may be felt. So technically, referred pain is visceral pain that can feel like it's coming from other parts of the body than where the stimulation is actually occurring. So this is why, for example, pain from heart attacks may be felt in the left shoulder. Stretching of tissues then cause pain sensations to arise from visceral organs. Pain in the lower esophagus or stomach or small intestine may be felt in the epigastric area, for example, that upper region of the stomach. Urogenital may be referred to as hypogastric. These are going to have less common nerve pathways. So again, this is a really good map to help understand where referred pain may possibly be coming from. So we have two different types of pain. We have acute pain and we have chronic pain. Acute pain, and these actually have different pain fibers associated with them, okay? So two different types of fibers that carry impulses from pain receptors. We have the acute pain fibers, which are called the alpha delta. These are going to be myelinated. So they're going to, that myelination is going to let them conduct the impulses very rapidly, up to 30 meters per second. We will often interpret or feel this as a sharp pain on the surface of the body. It's usually a local pain that stops after the stimulus stops, okay? So once you stop causing the pain, it does not continue to hurt. Chronic pain, or what we call C fibers, these are unmyelinated, so they travel much, much slower, usually only about 2 meters per second compared to the 30 meters per second for acute pain. And this is usually described as a dull, aching type of pain. This is usually going to be more widespread and difficult to pinpoint and often felt deeper in the body and can continue even after the stimulus ceases. Now, we become aware of that pain when the impulse reaches the thalamus. The cerebral cortex is going to measure the intensity and the source of the pain and then produce an appropriate response. Other portions of the brain are going to regulate the flow of pain impulses, such as the midbrain pons and medulla oblongata. Okay, so we have some pain inhibiting chemicals. All right, there's 3 of these here. We've got enkephalins. These are going to suppress both acute and chronic pain. These can relieve strong sensations similar to morphine and opiates. Next, we have serotonin, which stimulates neurons to release enkephalins. Okay. Endorphins now, these are our natural painkillers found in the pituitary and hypothalamus, and these are released in response to extreme pain. And so you've probably heard that somebody gets in an accident, their arm is cut in half, and while those endorphins are circulating, they're not feeling that pain. But once those endorphins wear off, then you begin to feel that pain. Serotonin, very interestingly, why do people cut? Well, because it does help to release, it's used in the healing process, and so it does help relieve pain. But we know serotonin is also going to have a biochemical effect on mood, and so people that are cutters are also getting a little bit of serotonin that helps their mood when they cut. So they're getting that positive reinforcement for that. So proprioception. Proprioceptors are mechanoreceptors that send information to your central nervous system, again, about body position, changes in muscle tissue. These receptors are going to include your Pacinian corpuscles, which are found in joints, muscle spindles, which are found in your skeletal muscles, and then what we call the Golgi tendon organs, which are, of course, in tendons. All right. Those two of these, the muscle spindles and the Golgi tendon organs, respond to changes in stretching, so we consider those stretch receptors as well. Stimulation of these do not necessarily produce pain, even though that's the category that they are in. Okay, so stretch receptors maintain, or they help maintain your posture. Okay. You can see these located here in the muscles, and you can see the Golgi tendon organ there on the right in the tendon. Stretch receptors increased muscle length is going to stimulate the muscle spindles and contraction, and for the Golgi tendon organ, it is going to be stimulated when the muscle tension increases. So those are found in tendons, and they can inhibit contraction. So as the muscles begin to tighten and tense up and increase, the Golgi tendon organ kind of can help them go back the opposite direction. Right, the visceral senses, these are receptors in internal organs. They convey information that is going to tell us when we are full. After we eat a meal, we get that if we eat too much, we get that discomfort. Or if you have gas pain, it can also be sometimes the pain associated with a heart attack. These receptors are going to be lamellated corpuscles and free nerve endings. This is a good summary here of the receptors of the general senses, including their function and sensation. These tables are always really, really good to study, so I would read over this and study this and be sure that you know the information on this particular table.